Imagine a robot navigating a cluttered room, trying to spot a specific object, like a red mug, without ever being explicitly told what a mug looks like. How would it do that? That's the challenge of open vocabulary 3D instance segmentation, a fancy way of saying, how do we help robots recognize and separate objects in 3D space, even if they've never seen them before? Today, we're diving into a groundbreaking method called OVMap, which tackles this problem head-on. Let's break it down. Traditional approaches to 3D mapping often hit a roadblock. Think of a 3D grid made of tiny cubes or voxels. When robots scan a scene, features from neighboring voxels can bleed into each other, blurring the lines between objects. It's like trying to tell apart two overlapping shadows. Everything gets messy. This makes it hard for robots to accurately identify individual objects, especially when asked to find something new. OVMap solves this by flipping the script. Instead of working with 3D voxels directly, it starts with 2D images. Here's the clever part. It uses a class-agnostic segmentation model, a tool that can spot objects in a photo without knowing what they are. These 2D masks are then projected into 3D space, like casting shadows onto a real-world scene. But wait, there's a twist. To make this work, the team created a supplemented depth image. Imagine a regular depth map, which tells you how far away objects are, but with gaps where sensors struggle, like on glass or reflective surfaces. They filled those gaps using synthetic depth data from a 3D point cloud. It's like giving the robot a superpower to see through tricky surfaces. Once the 3D masks are in place, OVMap uses a voting mechanism. Think of it as a group decision. Multiple 3D masks vote on which ones best match the scene. The strongest votes win, creating clean, precise object boundaries. This process avoids the need for 3D supervised models. No heavy training required. The results? OVMap outperforms existing methods on datasets like ScanNet200 and Replica, and it works in real-world settings too. Whether it's a messy kitchen or a crowded street, the robot can now spot objects it's never seen before, like a zero-shot detective. Why does this matter? Well, robots that can adapt to new environments without retraining are a huge leap forward. From warehouse automation to search and rescue missions, OVMap's open vocabulary approach opens doors to smarter, more flexible AI. So next time you see a robot navigating a complex space, remember, it might be powered by a little 3D magic called OVMap. Thanks for watching. Hit subscribe for more deep dives into the future of AI. Imagine you're looking at a 3D scan of a room. Your brain instantly recognizes objects, a chair, a table, a lamp. But how does a computer do this? Traditional methods often struggle with details, especially when objects are close together or partially hidden. That's where our new approach shines. The key innovation here is how we group and merge 3D data. Think of it like organizing a messy room. Each object, like a chair or a book, is a group. We calculate how much these groups overlap. If two groups overlap enough, we merge them. But here's the twist. We focus on larger groups first. Why? Because merging smaller groups too early can blur details, like mistaking a lamp for a table. Our method keeps the fine details intact. Now here's where it gets really smart. After merging, we use a dominant voting process. Picture this. Each area in the 3D space votes for the most likely object it belongs to. It's like a democracy. Every point in the scan gets a say. This ensures that even tricky areas, like a cluttered desk, are accurately segmented. But how do we make sure these segments are meaningful? Enter open vocabulary embeddings. This is where we assign scores to each group, based on how many pixels and points they have. It's like giving each object a confidence rating. Then we use AI models like Clip to add semantic meaning, so the system doesn't just see a chair, it knows it's a chair. The results? Let's talk numbers. On the ScanNet200 dataset, our method outperformed existing techniques, especially in rare categories, those tricky tail classes that other models often miss. On the Replica dataset, we saw a massive improvement, proving our approach works across different environments. And when we tested different depth data types, supplementing raw data with synthetic info boosted performance by over 7%. Here's what makes this research stand out. It's not just about accuracy. It's about adaptability. Unlike traditional methods, our approach doesn't rely on specific training data. It's like giving a robot the ability to recognize objects it's never seen before, whether it's a futuristic gadget or a quirky household item. So what's next? This technology could transform everything from autonomous vehicles to virtual reality. Imagine a robot navigating a construction site, identifying tools and hazards in real time. Or a VR system that dynamically labels every object in a digital twin of your home. Thanks for watching. If you're as excited about 3D AI as we are, hit that subscribe button. Let us know in the comments, what applications of 3D segmentation excite you? And remember, the future isn't just 2D, it's 3D, dynamic, and full of possibilities. Stay curious. Ever wondered how a robot could see and understand a room the way we do? Let's break down how our new method, OVMap, makes this possible. Imagine a robot exploring your living room. It needs to recognize a water purifier, a door, or a shelf, not just as blurry shapes but as distinct objects. Traditional systems rely on pre-labeled data, like teaching a robot, this is a door beforehand. But what if the robot could learn from descriptions alone? That's where Open Vocabulary AI shines. In our real-world tests, we captured 3D scans of an actual indoor space using RGB-D sensors. Think of them as cameras that also measure depth. These scans became detailed point clouds, like a digital 3D map of the room. Then we fed these maps into our system with simple text prompts, like "Find the refrigerator" or "Show me the shelf." Here's the magic. Our method didn't need prior labels. It used a special model that projects 2D object recognition, like what you see in a photo, into 3D space. Then a mask voting system refined the results, ensuring each object was precisely segmented. The outcome: perfectly separated instances of objects, even ones it had never seen before. Check out Figure 7. The robot identified a water purifier, door, and fridge purely from text queries. No pre-programmed labels, just smart AI. This isn't just about accuracy, it's about flexibility. Real-world environments are messy, full of unexpected objects. Our system adapts, making it a game changer for robots navigating homes, warehouses, or even disaster zones. So what's the big deal? OVMap isn't just another tech tweak. It's a leap toward robots that can understand their world in human terms. By combining 3D mapping with open vocabulary learning, we're paving the way for smarter, more versatile AI. This work isn't just about labs, it's about the future. Wherever robots need to see, learn, and adapt, OVMap could be the key. Stay tuned as we explore what's next in 3D AI.